There we go. Okay. So if you go into your class notebook, under 3.3a, you should have this note. Let's take it together. We're going to take a note. We're going to talk. This is normally what we do, like writing by hand, but instead we're going to do some typing. Okay, when you watch 3.2, you're going to see that the way stars form is dust and gas. That there are big clouds of dust and gas out in the universe. And just like a snowball, how do you make a snowball? Like for a big one, like if you're going to make a snowman or a snow fort, how do you make a snowball, a big one? What do you do?
Roll it in snow for like an hour.
Yeah, you just roll it and roll it. An hour, that could get real big. But when you roll it, it starts out as a little bit, and then as you get new snow, it sticks on and it gets bigger and bigger, right? That's how the stars form. There's dust and there's gas out in the universe, and when these things randomly collide into each other, they get a bit heavier, because now they're stuck together. And because they're heavier, they have more gravity, because that's how gravity works. The heavier you are, the more gravity you exert on other things. And if it exerts more gravity, then it pulls more things to it. And if it pulls more things to it, it gets bigger. And if it gets bigger, it has more gravity. Do we see how this works? And that process snowballs. It gets bigger and bigger and bigger. And as it gets bigger and bigger and bigger, as these things bump into each other and bump into each other and bump into each other, you know, if you take two objects and rub them together, which is what's going to happen when these gas clouds and dust clouds form together, what happens? You can do it right now. What do you experience? Yeah, which does what? Totally right. It creates heat. Beautiful. And so as these clouds form, if they get big enough and heavy enough, there's enough friction that eventually they ignite. We actually start a process called nuclear fusion, but essentially they start burning. And when that happens, we call it a... Supernova? Nope, not that. Much simpler than that. That's how we make a... Star. A star. That's how you make a star. A star is just you collect enough hydrogen gas that friction starts to heat it up and heat it up and heat it up, and it gets bigger and bigger like a snowball, and it gets bigger and bigger, which means more and more friction, which means hotter and hotter, and more gravity, which makes it get bigger, which means more friction, which makes it hotter, and eventually, if that happens enough, it gets hot enough that when the hydrogens hit each other, they don't just bounce off, they actually hit so hard because they're so hot that now they stick together and they make a helium. Don't worry too much about that. That's not the important part. The thing is, that process, what we call nuclear fusion, releases so much energy that the star begins to burn. Literally burn. It's out in space and now it's burning and it's hot. And it releases energy out to all around it. That's a star. That's how they form. And we watch that process. Well, very much related to that is how planets form. We said a star is what happens when it collects enough material that it gets big, 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 hotter, 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 until eventually it just starts burning spontaneously because of all that friction. A planet is when that same thing happens, but it doesn't get that big. Does that make sense? If it gets big enough that it starts burning, it becomes a star. If it doesn't get quite that big, and it doesn't become a star, it becomes what we call a planet, or a planet, I guess. I don't think anyone actually says that. So stars and planets form in the same process. They form in the same way. And we're going to say that in this little space here. And it's super annoying that that keyboard is so weird. So planets form from the same gas and dust clouds that stars do. Can everyone read my handwriting? I'm trying to be neat. Basically, if you look here, a star starts as a big cloud of dust that starts moving in, and we said that because of friction and because of gravity, it starts spinning. And you know this experimentally. Has anyone ever made pizza before from like just dough? Or even just seen it on like TV, where they take that dough and they throw it up in the air and they spin it. And when they spin it, what happens to the dough? It goes round, but what else does it? That's true. What else does it do? And this is why we throw it up and spin it. It doesn't just get round, which is good, but it also gets flat. Does that make sense? When you throw something and spin it, what's going to happen is in the axis in which it's spinning, it moves out and it flattens. So when stars start forming, because of friction, because of gravity, they start spinning. And as they start spinning, the middle part moves in and it starts making the star, and all the other gas flattens out. And eventually, just like that pizza spinning, it makes a disk. We call that an accretion disk. That's what we see here, is that this round ball of gas, as it starts spinning, will form into a disk. And because it forms into a disk, the things that are close to the center where the star is forming, gravity will pull them into the center. That gas and dust will become a part of the star. But the stuff around it, there's not enough gravity to pull it into the star, but there's also enough gravity to keep it from pulling away. And so they end up going in these very particular orbits. They spin, 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 not getting closer to the sun nor further, and they snowball in their own place. Can you imagine that? So basically, if you imagine this little bit of dust here is always spinning on this same path over and over and over again. And so it's going to slowly, 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 over millions of years, collect all of the dust and gas and rubble in just that pathway, and it'll get bigger and bigger. Does that make sense? And this piece of dust is going to do the same thing on that path. And this one, which I managed to use the same color, whoops, and this one will do the same thing with all the dust on that path. Because it's spinning around, it's slowly snowballing just on its own path. And each of those will eventually become a planet as they suck up all of the gas and all of the dust and all of the rubble in their spinning orbit. All of that gas and all that dust and all that rubble will eventually end up in just one place, and that one place will be that planet. Does that make sense? Kind of a cool process. I think it's cool. So we're going to write that down. We're going to keep it fairly short, but stars form from the dust collecting in the center, while a flat disk of dust and gas surrounds the forming star. And I'll give you time to write that. And if at any point I'm moving too quickly, just tell me. Because I get excited. Do you know that? Sometimes just talking about this stuff, I get excited. And so I want to move on. And then I go too quickly, and then people don't have time to write it. And then I feel bad. That makes me sad. So just tell me if I'm going too quickly. We call this disk an accretion disk. Nothing very magical about that name, but just that's what it's called. The disk is called an accretion disk, and so we say the planets or the particles in there accrete matter, which just means growing. It's kind of a weird word, but we can say this disk is called an accretion disk. Can somebody check? I've done it with 2 C's, and now that's making me nervous. Can somebody do a quick Google check on that for me? Can we see if that's how that's actually spelled, or if I've had a moment? I'm not always a great speller. I'm not super confident with my spelling. I got it. Sorry? What did I do? Center is an interesting thing because our American friends spell it this way, and our British friends spell it this way. And in Canada, we sort of are allowed to take our poison, pick our choose. So if you were to right-click that word and change it to the Canadian dictionary or the UK dictionary, it would tell you it's right. You can do either, just so you know. But as a rule, I will more often than not use the RE just because that's how I was taught. But yeah. Yes?
I always spell gray.
Do you do AY or EY?
I do both.
Yeah, I never know which one's supposed to be right. And so I just randomly pick between the two and hope that I'm doing okay. And I think maybe they're both right. I think maybe that's the answer. I think they're both okay.
In Minecraft, there's only one spelling for it, so I always spell the wrong one.
Oh. And I would imagine they're using the American, right? Like, I think Minecraft's made by Americans.
It's Swedish.
Is it Swedish? Oh, so who knows which one they use? But probably they still use the American, like, alphabet, or like a dictionary, rather, because most things do. Anyway, but thank you for letting me know that. And please, if I ever spell something wrong, please tell me, because it's kind of highly embarrassing to have a misspelled word hanging out in the teacher's notes. So, like, just mention it to me. You know, say like, no offense, but Orlando, you're really dumb with spelling. And I'll be like, oh, you're right. Okay, so the disk is called an accretion disk, and the planets snowball inside this accretion disk as it spins. Oh my goodness, my phone. Oh no, I meant to hang up. I'm hanging up. I don't want to talk to you. Whoever you are, I'm sorry. Are we all okay if I just keep the explanation pretty small like that? I mean, I could write like 3 whole pages describing it like step by step by step, but I don't really care that you know it in 3-page step by step by step detail. Basically, if you understand that this cloud of dust spins so it flattens out, and then as it spins, the middle becomes the biggest, heaviest part. That's going to give you the star. And on the outside, you get all these balls of gas and dust snowballing until eventually each of them becomes a planet. In some star systems, one of those planets that's orbiting will actually get big enough that it also becomes a second star. So there are plenty of solar systems out there that we've seen where not only does the central mass become a star, but another one out here becomes a star, and we call those binary star systems. There are some where 3 form. We call those trinary star systems. Those exist. Our planet Jupiter is really close to the size it would need to be a star. It is about 70% of the way there. If there had been a bit more gas and a bit more dust in its path when our solar system formed, it would have gotten big enough that it too would have started burning. Didn't happen. So what we have is a really big planet. What we could have had was 2 stars. I saw a couple hands up here. Yeah.
Does that mean that a planet could turn into a star? Like if stuff was living on it and then it just started burning one day?
Yeah, like theory. Like in theory, yes. In practice, no. Like keep in mind, the Earth gets a little bit bigger every year. Little bit, because what is always kind of bouncing into Earth? Asteroids, like constantly on a daily basis, right? Every time you see a shooting star, that's an asteroid hitting our atmosphere and coming down to Earth. So we get a bit more rock, but it's such a small amount that for practical purposes, no. That's the equivalent of like, as your hair gets longer, like as the hair on your chin gets longer, you get heavier. It's both true and not very important. You know what I mean? Unfortunately, I can't lose a lot of weight just by shaving. Be nice. Be like, 10 pounds lighter, but it just doesn't work that way. It's not much weight. And like asteroids hitting Earth, relative to the size of Earth, they're just so small. They don't really add a meaningful amount of mass. But in theory, yeah, if for some reason a massive amount of outside mass came in, yeah, it could get heavy enough. Having said that, the Earth itself is already somewhat cooled down from when it formed. I mean, tell that to the lava under the Earth, right? But it has cooled down some, though it is still quite hot from when it originally formed. It's kind of cool to think about. Great question, by the way.
If we had 2 stars, that would be catastrophic for us.
Yeah, well, especially because we'd be like between the 2 of them, so I don't think that'd go well for... Yeah, Earth would not have fared well, I don't think. I don't know much about orbital mechanics, but my instinct is that wouldn't have been good for Earth, no. And did I see your hand too? No? Okay, sorry about that. Okay, so that's the basic process. And the thing about a planet is if the solar system has been around long enough, it ends up sucking up all of the material, all of it, in its orbital path. Everything that used to be in that path becomes a part of that planet. Because if you leave it long enough, it's like the snowball. If you can imagine, if you went out to build a snowball and you went in the same circle over and over and over again with that snowball until eventually you'd soaked up all the snow, you would have, even though it was winter, you'd see like the green grass underneath, right? And then you could keep rolling that snowball all day, and would it get any bigger on that same circle? No, because you've eaten up all the snow. Does that make sense? That is how the orbiting planets work. They go in that same path over and over again until they've used up basically everything that's there. Every once in a while, though, you get times when two things on the same path had gotten pretty big. This is how we think Earth got its moon. There's pretty good evidence that the way Earth got its moon is that Earth was on its orbit, getting bigger and bigger and bigger, and in the same basic place, you had a second planet that was forming, a smaller one, and we've called it Theia. And Theia and Earth were forming in the same orbital path. But what's the problem with two big things being on the same place, same orbital path? What might happen one day? And as it happens, did happen.
Explosion.
Yeah, why? What happened to them? They're both forming, they're both on the same pathway, they're both getting bigger, they're both leading their happy little planet lives. And then one day,
They collided.
they collided, right? Right? They're on the same path, and all of a sudden it's like, this orbital path isn't big enough for the both of us, Theia. And Theia's like, oh, you think so, Earth? I think you're going to move first. But of course, because they're both just big lumps in rock, neither of them moved. And so they hit each other. Does that make sense? They collided. This was a catastrophic event. We still feel the effects of this collision today because the Earth actually isn't upright anymore as it orbits the sun. When the Earth first formed, because it's all spinning with the sun, right? Because it's all spinning, as it was made, the Earth spins around the sun, and it was all on a perfectly flat plane. Does that make sense? We were orbiting and spinning on the exact same plane that we'd been formed on, because why wouldn't we be? We were spinning how we'd always been spinning. And when this collision happened, Theia knocked Earth, literally, it hit hard enough that the whole planet went boom, like this. 23 degrees. It doesn't show it here, but 23-degree tilt. Earth is tilted 23 degrees on its side all the time relative to the sun, and we're pretty sure, scientists are mostly confident, that the reason that happened is because of the collision with Theia. And the cool thing is, Theia isn't our moon. It's not like Theia hit us and then it started orbiting us and it became our moon. Theia hit us, and both Theia and Earth just smashed up a huge plume of molten rock, right? Because that's a really massive collision. And that plume of massive molten rock and debris, that's what became our moon. Isn't that kind of cool? So the moon is part Theia, part Earth, 100% the result of this incredibly hard collision. Yeah?
So Theia beat us up so bad that we were crippled for life.
Well, we've hung on, but yeah, we got a bit of a, this would be the equivalent of if you got in a fight and for the rest of your life you walked around at a 23-degree angle, which I think we can all agree is about this much, and you'd look pretty weird.
Wait, so wouldn't the moon be Theia and Earth's child?
Yeah, there's a lot of there's a lot of sexual politics to break down in that comment that I don't really have time to get into, but I'm going to say no.
You aren't the fault.
I'm going to say I don't love that analogy. Yeah, there's a lot to break down there. Possibly none of it good. So we're going to move on. So we're just going to say this. Early in the solar system's life, more than one planet could form in an orbit. Though they would eventually collide. Our moon is the result of one such collision. as is that 23-degree tilt of the Earth's rotation. So the Earth used to rotate on the exact same axis that it moved on. And after collision with Theia, the Earth still moves on this axis, but now instead of moving straight up like that, it has been offset by 23 degrees. You don't have to draw that in, but... That 23-degree axis is going to turn out to be really important. We'll talk about why that makes a difference to Earth. But you feel that 23-degree rotation every day of your life.
The tides.
Turns out to be a really... No, though the tides are also related to this. You feel the tides because of the moon. Though, like, if you grew up living in, like, the Niagara region, you might not be all that aware of the tides. We're not too close to the oceans. Though you do... Yep.
Does our moon have a name?
Yeah, the moon.
Oh.
Isn't that lame? Sometimes it's given its Latin name, which is Luna. So some people think of it as that, but the official designation, at least in North American scientific literature, is it is the moon. There's other moons, but I feel like that's like I want to do one day. One day I'd like to be known as the teacher. Like there's lots of teachers at Eastdale. Who do you have for science? The teacher. People be like, what? Oh, the teacher. Not a teacher. Like Mr. Calford's a teacher. Mr. Reese's a teacher. But who teaches science? The teacher. You know, Jupiter has like tons of moons, but we have the moon. You see?
We have
That's
the
the thing.
Earth
Yeah.
moon.
Isn't one of Jupiter's moons called Titan?
Yeah,
I only know that because of Betelgeuse.
that's true.
That's it.
Yeah. The Jovian moons are its own interesting thing, and hopefully next week, if time permits, we have a lesson all about that. But you can see Titan if you have even just a cheap telescope. If you went on Kijiji and bought a telescope for $50 on the right night, you could point that thing at Jupiter, and not only would you be able to see Jupiter, which is pretty cool, like as a planet, but you can see the red spot on a good night right in Jupiter, but you can see the moons. You can see Titan orbiting it. Pretty cool. So this process is all the thing. The creation of our solar system was a messy, chaotic, really energetic process. Lots going on there. Something to keep in mind. We said these clouds were gas and dust, right? So some planets formed from gas and dust. And dust/rocks. Others formed from pretty much only gas. I'm just going to say only gas. That's not quite accurate, but pretty much. And so we have terms for these. We call the planets that formed from gas and dust, well, they're rocky. And they're made of like the Earth and things like that, like Earth. They're made of rock. And what is the Latin name for Earth? Does anyone know?
Isn't it dirt?
Nope, Latin. Latin, what do we got?
Earth?
It's a woman's name as well.
I forgot. I've heard it.
Isn't it like Terra?
It is. Very good. Terra is the Latin name for Earth, for rocks. And so the rocky planets, the ones that were made of dust, rocks, and gas, they're called the terrestrial planets. Terra means earth or rocks. If you spoke Latin, no science names would be confusing because they all just mean like, this literally means rocky planets. But, you know, scientists being fancy pants are like, oh, they're the terrestrial planets. They're just rocky. But they kind of gave up on the other one because you know what we call the ones that are made of gas? Yeah, gas. These are the two options. You have the terrestrial planets and the gas planets. In our solar system, do you know how many of each we have? Kind of interesting. Yeah. It is. Does that help you? Do you know now? We have an even split. We actually have 4 of each. And really interestingly, in our solar system, all of the close planets to the sun, well, because the sun was the heavy part, the heavy things started to move in mostly to the middle. And so the 4 planets closest to the sun are made mostly of rock. They're the terrestrial planets. And so for some reason, I've put the picture of them second. That was stupid. But these are the terrestrial planets. And this slightly reddish fellow here, we know that to be, yeah, the sun itself would be here. Hey, look at me, I'm a happy sun. This is Mars. Our fun blue fellow here, Earth. What comes after Earth? This planet is the same size as the Earth. Fascinating. Almost identical, a little tiny bit smaller. Yeah.
Venus.
Very good.
Earth's little sister.
That's right. Well, pretty much the same size. And then this fella here, this chaotic, extremely hot, close to the sun, nutso planet.
The moon.
No, this is not the moon. It is Mercury. Good. So those are the terrestrial planets: Mars, Earth, Venus, and Mercury. And they are closest to the sun. When I took astronomy in university, I had this professor named Bozidar Mitrovic. And he would always say, he was like Eastern European, and he'd say, the sun. So he'd say, and so these are planets that are closest to the sun. It was always this weird the sun. And I always, whenever I teach this now, I think of that. Oh, Bozidar. He was a great professor. He was really good. And then, if we imagine Earth to be here, there's happy little Earth. And then further out, there's Mars. What colors do I use? Not that it matters. I use blue for Earth. I guess that makes sense. We got all that water. Then I used blue for, that makes no sense. And then like here's the sun. What are these guys? Who's this? These are the gas giants. Who's this guy? Yep.
Jupiter.
That's Jupiter. And who is this lovely fella here?
Saturn.
That is Saturn. Well known for its highly visible rings. Not the only planet with rings, but it's got the nice visible ones. Again, with not a very expensive telescope, on a good night, you can point up at Saturn, you can see the rings. Pretty amazing. Kind of life-changing. Like really, there's something about looking at something that's just a dot in the sky, and then when you look through a piece of plastic and glass, you're like, holy crow, it's a planet and it has rings. It's kind of life-changing. I highly recommend it. What's this guy? Neptune. Good. What's this guy? Uranus. Very good. So we've got Jupiter, Saturn, Uranus, and Neptune. These are the gas giants. And again, Jupiter is so big that she almost a sun. Big old planet. The gas planets are giants. They are much bigger, much bigger around than the terrestrial planets. Can I go on to the orbits, or do we name it?
What about Pluto? I don't see
Not a planet. We'll talk about that.
Oh,
It's a dwarf planet. It's
All right. The orbits are
Say
all...
that to Pluto's face. Say that he's a dwarf planet.
The planets orbit in ellipses. What's an ellipse?
I think of that word.
Ovals. Though most are close to circular. If you just look briefly at the orbits, they look kind of like circles, but they're actually ellipses. They're actually all ovals. You can definitely see that more so with Pluto and with Eris and with the dwarf planets that are further out. They're kind of more obviously ellipses, but even if you look at Mars, Mars is pretty clearly not a perfect circle, right? Can everyone see that? Cool. So the planets orbit the sun in ellipses, ovals, though most are close to circles, and they all orbit in the same direction, which makes sense because they all formed from that same spinning disk of gas, right? So all the planets are orbiting in the same way that disk was spinning. All orbit in the same direction. And the last question we'll ask, and this will lead us into the break, is why not Pluto? Why didn't I put Pluto in here? What might you think? We call Pluto a dwarf planet. Why So Pluto is a dwarf planet. Why do we call it that? What does not make it a planet then? What are the definitions of a planet? Just based on that name, what do you think the problem is?
I think in order to be a planet, you have to be orbiting the sun, have your own gravity, and clear your own neighborhood.
Yeah, that's right. This is a boring answer. I was hoping you'd say something wrong, then I could correct you. Yeah, you're totally right. That's good. There's 3 things that you have to be a planet. All right? So the name dwarf makes you think that I'm going to say that Pluto is just too
Tiny.
Yeah, but that's not it. Pluto is actually more than big enough to be a planet. Size is not the issue. So here are the 3 things you need to be a planet. 3 things that make a planet.
Atmosphere? No.
Nope, not necessarily. And this may take us 2 minutes into the break. If you don't mind, just let me finish and you can have the extra time in the break. Does that make sense? It just seems a shame because it might take 2 or 3 minutes, and it's a shame to just have to come back and finish that. So I promise you'll get your break time. You can stay beyond the bell, but let's just get this done. So 3 things that make a planet. 1, it has to be massive enough to form a sphere from its own gravity. All right, that has to be rule 1. You can only be a planet if you're big enough that your gravity has pulled things in to basically be a sphere. And the Earth is really close to being a perfect sphere. Because of its spinning, it's a little tucked in, or it's a little fat in the middle. So the Earth actually, because of its spin, the mass in the middle kind of gets pushed out a little bit. So Earth has a little bulge. It's a little more bulged than perfect sphere at the equator. But it's really close. It's pretty close to a perfect circle. And that's because if you get big enough, gravity pulls on things and everything wants to get as close to the middle as possible. And what shape gets everything as close to the middle as possible? A sphere. If you're trying to pack things so that everything gets as close to that center point, you can't pack closer than a sphere. So that's the first rule. Massive enough to form a sphere from its own gravity. Okay, and just for the record, Pluto is. The second thing is, to be a planet, you have to have formed when our solar system formed from that big disk of gas and dust that was spinning around the center mass. And so if you're a planet, you have to also be spinning around the center of that sphere of dust. And what's now at the center of that sphere? What formed in the center of that big accretion disk of dust and gas? Good. So the second thing is it must orbit the sun. Does Pluto orbit the sun? Yep. So it has to have an elliptical orbit around the sun. Pluto does. So Pluto is big enough. Pluto orbits the sun like a planet. Why isn't Pluto a planet? Got those 2 things going on. Well, remember we said when the Earth was still forming, it had a major event. What was the big major event that had big major repercussions for Earth? Yeah, it collided with that other protoplanet Eris. They were both in the same orbit. Yeah, that's right. Knock them out, and it's still all tilty. Hasn't recovered, 5 billion years later. Not 5. Yeah, I guess about 5. So 5 billion years and he's still not over. Earth knows how to hold a grudge, man. But the reason that happened is that as Earth was orbiting the sun, it wasn't the only thing there. It wasn't the only thing in that orbit. Eris was there. We didn't consider them planets either in kind of the way we think of the cosmology, the way we think of the formation. At that time, we would think of both Eris and Earth as what we'd call protoplanets. Not yet planets, forming planets. Because one of the things Earth had to do before we consider it a planet is what we call clear its orbit. In other words, it has to be the only big thing in its orbit. Does that make sense? So the third thing is it must clear its orbit, which means be the only thing that is big, massive, and substantial in its orbit. and Pluto doesn't. It's funny because everyone always cries about Pluto. Pluto isn't even the biggest dwarf planet. There are other bigger, more massive dwarf planets out there floating around, and they never get any attention because everyone cries about Pluto. Why isn't Pluto a planet? Poor Pluto. To which I say, what about Eris? By the way, I was accidentally saying Eris was what collided with Earth, but that was Thea. I'm sorry about that. I got my names mixed up. But like Eris is out there. It's got a bigger orbit than Pluto, but it actually gets closer to us than Pluto does at various points. And he's a big old dwarf planet too. Nobody cries about Eris. You don't see any online petitions to make Eris a planet. I'm just saying. Why does Pluto get all the love?
Wasn't Pluto originally called a planet?
Yeah, it was. But it's probably not such a big controversy for you. But I grew up knowing that there were 9 planets, and Pluto was the last one. And then one day they were just like, nope, only 8. And everyone was like, what? But this is why. We discovered other dwarf planets. See, Pluto was the furthest planet away that we had ever discovered. We thought, that's amazing. Here's this tiny little planet. It's dark because it's far away from the sun, so it doesn't get shined up very much. And when we built big enough, sensitive enough telescopes, we were able to actually track it and learn about it. We've actually sent probes out to take photos of it. They're amazing. But then we discovered it's actually one of several protoplanets, dwarf planets in its orbit. And so it doesn't classify as a planet under the modern classification system. It doesn't mean it's any less interesting. The cool thing is, since then, in your lifetime, we have found planets around other stars. So we now have seen not only planets around our solar system, but we have seen planets around other stars. Now, we can't take photos of them because it's impossible, but we've detected them. When next week, you will actually do a little citizen astronomy project where you learn how we detect them, and you'll actually look at some evidence of exoplanets yourself. You're going to do some real astronomy. You're going to look at real data. And when I say real astronomy, I mean you're going to be doing astronomy where NASA is actually collecting the data you interpret and pooling it with millions of other people interpreting data to build a database from which they make actual discoveries. Pretty cool. Neat opportunity. Yeah, you have a question.
I don't remember if this was last year or the year before, but haven't we also found a sister galaxy or something?
Many.
Because I remember whenever it was radio waves or something.
Yeah, so just understand, and when you watch the lesson on the scale of the universe, you'll get a sense of it, but there are hundreds of trillions of galaxies out there, which is crazy. Each of those galaxies contains hundreds of trillions of stars, which is crazy. And then each of those stars has planets around them. Some have less than we do, we think. Some have more than we do, we think. But just think how many huge, massive things there are out there. It is truly mind-boggling. And then what's even more mind-boggling is it's mostly just empty space. Our nearest solar neighbor is a star called Proxima Centauri. Closest one away. So it's the closest star to us. And it's so far away that the light it shines takes, I think, 2.3 years to get to us. That's how far away. It's so far away that light travels 300,000 kilometers every single second. It takes the light from Proxima Centauri, our closest neighbor, 2.3 years to get to us. It's wild. It's a wild number. It's a wild scale to think about. The furthest thing we have sent out is a probe called Voyager 2. It was the first probe we launched in the Voyager program. The second probe we launched in the Voyager program was called Voyager 1. There's some weird naming going on, but that's all right. But it's the thing furthest away from Earth. By all accounts, it has left our solar system. It will be thousands of years before it even comes close to another star. Mind-boggling how long it takes to go from place to place. The universe is a very big place. But the thing is, it's all so far away that we can't go to it, so we need to collect information that it sends to us. And we do that with telescopes. We do that with radio telescopes and radio receivers and X-ray transceivers and all these different tools that we use to take the information they're sending to us and analyze it. The crazy thing is, our universe is 13 billion years old. And so some of the things we're looking at, that light has been traveling 13 billion years to get to us. We are seeing stars up in the night sky that have actually been dead for billions of years, but they're still shining in our sky because the light's still traveling because it takes so long to move. It's pretty crazy. It's a crazy thing to think about. So I love this. I could teach a whole course on this unit. I would love to teach a whole course on this unit, but I can't. But what we can do is hopefully get into it. So that's the end of this lesson, and I made it for break time. Look at me. I'm so good. You're welcome. But there's some follow-up questions there. Can I quickly ask you, there's actually only one follow-up question for this one now that I think about it. Would you rather I do the next lesson right in block 2 and then I'm done for the day? Or would you rather have block 2 to kind of work and then I do the lesson in block 3? I'm flexible either way. Hands up if you want me to just, after the break, we do the next lesson in block 2 and then you're on your own for the day. Hands up. All right, 1. Hands up if you would rather I teach the lesson in block 3. 3 hands. That's the winner. All right, there we go. So in block 2, you'll have time just to get caught up on 3.1, 3.2, finish the follow-up question from 3.3, and then in the third block, we will teach the final lesson. All right? All right.